Okay, remembering that this is just a carbon cycle primer, we have not gone into many details here in this course. So this is close to the end of the carbon cycle part, and we will jump to methane in the next chapter and close it out. But one thing that remains here is then the perturbation or the blob of CO2 we are putting as fossil fuel CO2 into the system, and try to see what happens to it in the carbon cycle, which has all these nice multiple time scales with all its moods, as we call them, positive feedbacks and negative feedbacks. Archer, the author of this book, David Archer himself, has done some nice work on this, so I'm just going to take a couple of brief ideas from it just to then bring us back to what we may want to do in the coming coming decades to handle this situation. Just to remind ourselves, the carbon sink reactions, of course, there is the seawater buffer, CO2 plus CO3 minus plus water was giving us 2HCO3 minus dissolved in the ocean. Remember that there is much more, 100 times more HCO3 minus in the water than CO2, and 10 times more CO3 minus, but as we keep putting more CO2 into the ocean, it's going to keep consuming CO3 minus and cause acidification and dissolution of corals and other calcium carbonate forming organisms like coccoliths and forams and so on. So that's a fairly fast reaction, the calcium carbonate pH stat that we called it. And then, sorry, that's the ocean acidification or buffering, seawater buffering reaction. The calcium carbonate pH stat reaction is basically going to demand that the CO2 increase in the water will obviously directly decrease the pH, and that's going to be tried to be compensated by calcium carbonate dissolution, and that's going to split calcium carbonate and again give us bicarbonate, right? So this we didn't want. On a long time scale, this reaction is compensated by calcium carbonate input from land weathering reactions and just washing down material, but if we keep increasing CO2 rapidly, that's going to be a problem. But let's say we all got wise and we stopped fossil fuel emissions in about how many years? 50 years? Okay. Then we have left a slug of CO2, fossil fuel CO2, since Industrial Revolution, and the question is then how long these reactions will take to decide the fate of that fossil fuel CO2 in the carbon cycle. Then there is a very long time silicate weathering CO2 thermostat reaction, which goes this way. CO2 plus calcium silicate gave us calcium carbonate plus SiO2 in the ocean sediments, which over time on temperature and pressure become calcium carbonate or limestone, which get exposed by plate tectonic activities and then weather down and so on and so forth. So what is the time scale of this slug? So Archer did a lot of work on this. This is from his paper, used multiple models with various details of carbon cycle, including calcite chemistry and calcium carbonate pH stat and so on and so forth. And he looks at a couple of slugs of or pulses of CO2. So he's looking at 1,000 paragram carbon pulse, like the pulse we saw in the case of the Paleocene-Eocene thermal maximum, and the 5,000 paragram carbon pulse, and looks at the equilibration time in years with the various methods by using the base scenario where there are no feedbacks in the carbon cycle and the ocean circulation, pH and other things, and then you have feedbacks of all the processes that we talked about. Okay, so A is the equilibration time for CO2 invasion into the ocean, and B is the equilibrium airborne fraction of CO2 after ocean invasion for cases with no sediment interaction. That's the base case, and In C, we have calcium carbonate dissolution response time in terms of sediment interactions and predicted present-day CO2 uptake rates when models are subjected to historical atmospheric CO2 concentrations. So the real ocean now takes up about 2.2 petagram carbon per year between the comparable time intervals 1990 and 2000. So the models are constrained in some way, or at least chosen in some way. So all I wanted to point out is that you can look at the time scales here. We talked about the residence time and so on. But CO2 in the ocean is complicated. It's not only doing the buffering reactions and the inorganic chemistry, calcium carbonate, pH stat and so on, but it's also involved in biology, export of organic carbon, sediment interactions with microbes and so on and so forth. So you can have various details of interactions. So equilibrium airborne fraction in each case, in each model with 1000 petagram carbon pulse and 5000 petagram carbon pulse is shown here. So the scales are different, so you have to be careful. This is 450 years, this is here 1400 years, this is 30%, and this is 60%, and so on. So this here is up to 50%, this is less than 30%, etc., etc. Okay, so that's with feedbacks. You get higher fraction of CO2 remaining in the atmosphere. So this gives you a hint that over equilibration time scale of many hundred years or many hundreds of years, depending on how much carbon we put into the system, the carbon cycle with feedbacks is going to give us more carbon than the base case where there are no feedbacks. So we have to be careful about that in terms of the stability of the carbon cycle that we were discussing. And this is for the 1990 to 2000 case, calcium carbonate response time scales. This is the historical case. This is the same thing with calcium carbonate pH stat time scale of what's happening in the ocean in terms of controlling pH for 1000 petagrams and for 5000, and you can see there are large differences. This one has much longer calcium carbonate response time scale for 1000 petagram carbon pulse than the 5000 one, but this one has higher but smaller for 1000 than 5000 and so on. So obviously there are uncertainties in the models, and some models don't even do that because there are the complexities of the biological representation and the chemical cycle representation. The organic and inorganic carbon cycles are done very differently. In other words, not only do we have gaps in understanding of the feedbacks, but also gaps in the representations in the models and their effect on what to expect. Okay. Nonetheless, here are the historical emissions uptakes in petagram carbon per year, and you can see some are way down here in petagram carbon per year, but many are up here, and the observational real ocean estimate is at 2.2 petagram carbon per year. So that's what we have been seeing in those time series figures we've been looking at. Some do much higher, some do much lower, and some are much more realistic. So you have the problem on hand. With all this information we have so far, what does it mean? So in going back to our emissions, business as usual is going to put us in this range in terms of the warming. And so there are two things we're trying to deal with, right? We are doing certain emissions, fossil fuel burning, energy usage, energy production, etc., land use change as well. And then there is the global warming target we are trying to stay within, because from the past we know that warming above that range is going to create too many problems. So then we have to translate between CO2 and warming targets. That's always the difficulty, and that's the challenge. So here we are at 2100. To stay for below 2 degrees centigrade pathway or 1.5 degrees centigrade pathway, with a certain probability, let's say 66% or 50%, we have to start reducing emissions below 50 gigatons, where we are already approaching by 2020, 2021. And we have to do it very rapidly. We are already behind. We are already on this target instead. And there are other ranges here, but the current policies only get us to this level here. The pledges and targets under Paris Agreement bring us down a little bit, but that's still much further away from the 2 degrees C or 1.5 degrees C pathways. So this is the manipulation of the carbon cycle that will be needed to hit the global warming target. So it's not just what happens to carbon cycle, but what are we going to do to the carbon cycle to obey our orders to stay on these pathways, not only in terms of emissions reductions, but also drawing down carbon from the air with carbon capture and sequestration, or carbon capture and utilization ideas. So the later we go without drawing down, the faster we have to draw down the CO2 to hit these targets by 2050 and 2100. Obvious, right? So if we keep continuing to emit and do the remediation later, we're going to have to change the rates much faster, and this is to stay below 1.5, which is much larger drawdown needed. This is for 2 degrees centigrade, which is somewhat slower, but still faster if you delay the action. Makes sense. The other thing that we have to watch out for is what the Earth's natural climate is going to do in terms of ice ages. Typically, if you look in the past, ice ages lasted for 100,000 years time scale in the Pleistocene, or the last million years. But the deglacial periods like the present lasted only 10,000 years, which we have already crossed in terms of the Holocene, plus we are increasing carbon emissions. And then there are orbital parameters. So you have the ellipticity, which is changing at 100,000 to 400,000 year time scales, the tilt, which changes on 41,000 year time scales, and precession, the wobbling, which changes on 26,000 year time scale. There is another precession called the apsidal precession, where the equinoxes and the solstices change in terms of the time of the year when they occur. Altogether, the net amount of annual radiation received is not going to change much by these changes in precession and tilt and eccentricity. Eccentricity change is too small, even though the distance changes, but eccentricity tends to modify the precession and give you time scales. So currently we are in a more circular orbit, which means the radiation received, it doesn't change that much throughout the year from the distance itself. But the tilt changes the seasonal distribution hemispherically. So in this configuration, the interglacial periods tend to remain longer, and then there is the carbon cycle perturbation. So we have to consider all those things to see how we are changing the natural variability of the ice age and glacial deglacial variabilities as well. The other thing we are doing as I'm sitting here and recording this is that India is having a tsunami of COVID, lockdowns, reduced production, reduced traveling, etc. So 2019 to 2020 saw a large drop in GDPs, energy demand, and CO2 emissions, but CO2 emissions have already begun to catch up, and GDPs are increasing, and countries are trying very hard to ramp up the GDPs again to keep the economic growth going. Energy demand is going up and CO2 emissions are going up. So we are not really anywhere on the targets of wanting to reduce total emissions despite the negotiations, especially now with US again taking or wanting to take leadership and so on. Good news is that coal burning is going down, still very high in terms of the electricity generation, but the low carbon options are now becoming larger than the coal energy production, which is good news. But again, keeping in mind the emissions, we are still a long way to go. So solar, wind, other renewables, nuclear, hydrocarbon, hydroelectric, and so on are still not completely replacing coal as fast as we should. So that's where the future is. So we will stop there and then look at methane in the next chapter.